Welcome to section 5.1, Discrete Random Variables. In this section, we're going to learn how to describe the behavior of numerical outcomes that arise from random processes, from games of chance to insurance models to the number of times a customer visits a store. These variables help us quantify uncertainty and analyze risks and rewards. By the end of this section, you'll be comfortable with discrete probability distributions, expected values, and standard deviations, and you'll see how these concepts play out in different scenarios. A random variable is just a numerical value assigned to the outcome of a random event, like flipping a fair coin. Instead of thinking about outcomes like heads or tails, we assign numbers like 0 for tails and 1 for heads. That lets us calculate averages, variances, and more. Let's take the example of flipping 2 coins. If we define x to be the number of heads we observe, then the possible outcomes of the experiment, we could have heads, heads, so a total of 2 heads. Heads, tails, a total of 1 head. Tails, head, a total of 1 head. And tails, tails, or 0 heads when we flip the 2 coins. So that translates to these values of x being possible. X equals 0, 1, or 2. Each time you repeat the experiment, x could be a different value. That's why it's called a random variable. Random variables come in 2 main types, discrete and continuous. A discrete random variable has countable outcomes, like the number of Marvel movies someone has seen, or how many sodas a student buys at the cafeteria. You can list the outcomes one by one. In contrast, a continuous random variable takes on values in an unbroken interval, like a student's commute time or the weight of a delivery box. These values are measured, not counted. In this section, we're focusing on discrete variables, which are very common in business, marketing, and everyday decision-making. A probability distribution tells us all the possible values of a discrete random variable and the probability associated with each one. Think of it as a full list of what could happen and how likely each outcome is. 2 rules must be met. First, each probability must be between 0 and 1. Second, the probabilities must add up to exactly 1. If those rules aren't followed, it's not a valid distribution. The list allows us to make inferences and decisions, like choosing a product to stock based on expected sales. Let's revisit our earlier example. You flip 2 fair coins. The outcomes are, whoops, go back. Too much. There we go. I lost my pen. Let's get that back. Our outcomes are tails, 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 heads, heads, tails, or heads, heads. 4 possible outcomes. So the probability of 0 heads only happens 1 out of 4 times. 1/4 is 0.25. The outcome of 1 head happens twice out of 4. 2 out of 4 is 0.5. And the probability of 2 heads happens once out of 4 times. So its probability is 0.25 again. This forms a valid discrete probability distribution. It adds up to 1, and each probability is between 0 and 1. This type of setup is the foundation of many games of chance, and the same logic applies to evaluating risk, marketing surveys, and decision trees. So we got the probability distribution there. All right. We can also graph a discrete probability distribution. The x-axis shows the possible values of the random variable, like 0, 1, 2 heads. And the y-axis shows the probability of each. So we have our head 0, 1, and 2, and the probabilities 0, 1/4, and 1/2. Each value gets a bar. And often with the discrete distributions, the bars won't touch. Here in this example, we have our bars touching. But when they don't, that's one way to visually distinguish a discrete distribution from a continuous one. The total area under the bars still represents the whole, the entire sample space. So the probabilities must sum to 1. Now let's calculate something very useful, the expected value or mean. This is what we'd expect the long-run average outcome to be if we repeated the random process many times. So our formula is the expected value is equal to the sum of the events times their probabilities. In our coin example, the outcome of 0 times its probability of 0.25, the outcome of 1 heads times its probability 0.5, and the outcome of 2 heads times its probability 0.25. Now notice that would be 0 plus 0.5 plus 0.5, so we'd get a 1. So if we flip 2 coins over and over, on average, we'd expect 1 head per pair of flips. This idea of expected value is crucial in business, like estimating average returns or average claims per customer in insurance. Excuse me. Now, while the expected value tells us the average, we also want to know how much the values vary around that average. That's where standard deviation comes in. The formula is sigma, lowercase, right, equals square root of the sum of our outcome minus the mean squared times the probability associated with it. It gives us a sense of how spread out the values are. A high standard deviation means the outcomes are more variable. A low standard deviation means they're tightly clustered near the mean. Think of stock prices. Some stocks are stable with low standard deviation, while others are more volatile. This same reasoning applies to customer behavior, inventory needs, and financial risk. Now, on the last slide, we calculated the mean or expected value and found, for that example, mu was equal to 1. That was for the number of heads in 2 coin flips. Now, we also had the probability distribution, right? We found that the probability of 0 heads was equal to 0.25. The probability of 1 head was equal to 0.5. And the probability of 2 heads was equal to 0.25. All right, so let's plug into this formula. So first of all, to plug into this formula, we're going to do the observation x. So in this case, our first outcome is a 0 minus the mean of 1 squared times the probability of the 0 heads, that's 0.25, then plus the outcome of 1 head minus the mean squared times its probability, plus the outcome of 2 heads minus the mean squared times its probability. All right, so that is the square root of, this would be 1 times 0.25, plus that would be 0, so that whole term would be 0. That would be 1 times 0.25. So we would get the square root of 0.5, which is about 0.707. Okay, so we found the mean was 1. The variance is what we get before we take the square root. So that's right here. So our variance, sigma squared, is 0.5. And the standard deviation, sigma, is 0.707. All right, let's do this with Excel. I'm going to, very simple example, show you how we got that. All right, I've already put the outcome, 0 heads, 1 head, 2 heads, and the associated probability. 0 heads happens 0.25. 1 head happens 0.5 of the time, right? And 2 heads, 0.25. All right, so to get x times p of x, we're just going to multiply a2 times b2. And then I can go and grab this corner and drag down to fill in the formula, right? And it automatically adjusts the formula, right? It goes to the next cell. All right, so to get the mean, remember, the mean is just the sum of these probabilities. So we're just going to add up sum C2 to C4. Now, x minus mu, and then we're going to square it. So the x is here in A2. But I want the mean, which is right here, not to change when I move my formula. So to keep it the same, I'm going to use the $sign to keep the position static there. But now I needed parentheses around this because we're going to square it. So parentheses, close parentheses, and square. Now I can drag my formula and see it'll automatically fill in and just this number rotates, but the C6 stays the same, okay? Okay, so now we need to multiply that times its probability, then add them all up to get the variance, right? So we're going to go D2 times the probability is in B2. And let's bring that down. So our variance would be the sum E2 to E4. And the standard deviation would be the square root of that variance. And there's our 0.707 that we found in the slides. Suppose a pop-up Marvel merchandise shop wants to predict sales of Spider-Man plushies. Let's say the number sold in a day, X, can be 0 through 5, with associated probabilities from stored data. With that distribution, we could compute the expected number sold, mu, the mean, to guide inventory planning. We could calculate the standard deviation, sigma, to know how much sales might fluctuate. This helps the manager avoid overstocking or underselling and ensures fans can always get their friendly neighborhood spider plush. Let's apply this to risk assessment. Suppose an insurance company offers event cancellation insurance. The event has a 2% chance of being canceled, and if it is, they pay out $100,000. The company collects a premium C if the event isn't canceled. To break even, the expected profit should be 0. So our expected profit would be 0.98 times the premium, right? Because 98% of the time the event will be held, plus 0.02, the number of times it's going to be the probability of it being canceled, times our premium, right? So C minus the 100,000. Set that equal to 0, and then solving this equation, gives the minimum premium they must charge so that they don't lose money on average. This is exactly how real-world insurers determine policy prices, by modeling rare events and expected payouts. So to summarize, discrete random variables model outcomes we can count, like sales or survey responses. We use probability distributions to describe how likely each value is. The expected value tells us the long-run average outcome. The standard deviation tells us how much variation to expect. These tools allow businesses to make data-informed decisions, from how much stock to order to how to price policies to how to predict customer behavior. And as you've seen, the same math that describes coin flips and insurance also underlies the logic of how you manage your fantasy league or guess how many Marvel movies someone has seen. These models help us reason with uncertainty, which is the heart of statistics.